Thank you for joining the discussion on information chains. And in this discussion, I hope we can uncover some insights into information chains in discontinuum mechanics. So typically in discontinuum mechanics, we have force chains, and that's particularly for spherical particle systems. The discussion I'm going to have today is to talk about why we have to go beyond the force chains and really look at information chains to get deeper and better understanding. My name is Daniel N. Wilk from the University of Pretoria in South Africa, and joining us for the discussion today is Patrick Pitset from IMT North Europe in France. So discontinuum mechanics really is just the mechanics of particulates or particles or material, separate pieces of material that interact with each other, where we would like to understand that interaction and the phenomena that it can result into, the flow phenomena, the consolidated phenomena. And we want to try and get as much insight as we can into what is going on in these phenomena. So as an example, we might have a hopper of 300,000 particles as illustrated that is emptying. And we would like to know what interactions there are between these particles as they flow out of the hopper. And also understand what is the final consolidated state that it would reach. Alternatively, we could have discontinuum embedded in continuum systems. Here we have gray particles embedded in white fluid particles from an SPH model, working in conjunction with IMT. And now we have interaction between the discontinua with each other as well as with a continuum system. And this is typically the mechanics that we would like to try and understand better, and that are also relevant for additive manufacturing processes. So classically, contact forces is what's used. We can compute contact forces between particles because we have force laws between particles. So typically, if I have two spherical particle systems interacting, I might have a certain force law that changes as unit distance that might be nonlinear. I might have a variation of contact area and contact volume as a function of penetration distance. And the mean pressure that might be resulting, depending on the model that we have, might vary as a function of penetration distance. But what is important here is that penetration distance defines each of these states uniquely. This is in essence what we have for a typical nonlinear force model. Later on, we're going to talk really about a linear spring dashpot system, which is the simplest model that we can have, and then see what kind of insights we can derive for just a spherical system. As soon as we go towards non-spherical systems, we have to go beyond force chains. And this example is really just to convince you why that's necessary. If I were to look at the top example, the contact force in each of these cases are essentially the same. The magnitude of the contact force is the same because the penetration distance is the same. But what we know is the pressure at the contact would vary because the area was varying between the three scenarios. So just out of this, beyond a constant curvature interaction between two spheres, we all of a sudden have to go beyond just force chains, just because it doesn't capture all this information that is actually required to understand what's going on in mechanics. In the bottom scenario, what we have there in essence is a constant volume overlap. But what I'm showing you is the penetration distance is vastly different in those three scenarios, although the volume are the same. And so this is just to convince you why we need to move beyond just penetration distance to get deeper and deeper insights. Okay, so forces versus traction. So this is our first example of just two information chains. One is just looking at contact force, and the other one is going to look at traction, or think of it as mean pressure between particles for now. And what I want to show you is if we just focused on force chains, we would just conclude that the forces are the same between these three scenarios, and so nothing more to learn. But as soon as we look at traction change, what we see is a gradual increase in traction because the contact area is decreasing, although the force remains constant. And this is all additional information that we get from this particle system just because we looked beyond the force chain towards information chains, and then specifically chains that might be useful information for us. So let's look at a practical example of more stacking of 6 random stacked particles, again, of forces on the left and fractions on the right. And if you think about contact pressure as the primary driver for degradation of particles properties, then what we would conclude is, by looking at where the pressure is high on the right, we would conclude a very different picture of where we have degradation versus the left, where we might just look at the force magnitudes and conclude large driving contact forces to drive degradation, which is in many cases not the case. So although contact force is often used as a driver for degradation in particle systems in discrete element modeling, we have to move beyond that towards pressures that are the primary driver for most of the degradation that one might encounter. So a larger system now, beyond the 6 non-spherical, let's go back to the simple spherical particle system, linear spring dashboard system, no friction and no damping. And let's look at 3 information chains: area, contact force, and traction, and see if we can learn a picture from this that might be interesting. So essentially we have a tilt box. The gray area, the dark gray area, is where the particles will be falling in, and then the particles fall, hit the bottom, and roll down to the bottom. And captured at a certain stage, just 1 or 2 seconds into this simulation, what I'm capturing there is just where are the contact areas large and where are they small. And I would like you to focus on the ones where they are large. As we go towards the right-hand slide, where I'm going to show you now forces and traction, I just want you to focus on the forces for now and compare where there's large areas with where there are large forces. And if we do that, the picture on the left, we see where we had large areas, we also have large forces. And that is in essence what we learned from looking at contact area and contact forces in isolation. If we were to compute the traction, or the mean contact pressure, just as the force divided by the area, what we see is a constant contact pressure, irrespective of the penetration distance. It's because the rate at which the contact force grows and the rate at which the contact area grows is the same. And that's why we end up with a constant traction system. So the contact pressure for a linear spring dashboard system with no damping and no friction is constant, irrespective of the penetration distance. Now we can conclude how useful would a linear spring dashboard system be, for instance, if we were to like to track particle degradation. And we can immediately see that it might not be sufficient at all because of the fact that the traction or the contact pressure remains essentially constant. For the purpose of this talk, I'm going to think of contact traction and contact pressure as equivalent, although they are not at all. Traction is very different to pressure, but I'm just going to compare magnitudes for now, and then we can think of them as being equivalent. If we have now a particle system, same system, linear spring dashboard, also spheres, and I've just added now friction and damping as opposed to only no damping and no friction. So here we switch it on now. In essence, what we see now is the contact forces are now where they are large. And if I look on the traction side, all of a sudden it's not constant anymore. There's variation in the tractions. And that's because all of a sudden there's different mechanisms at play. There's now damping at play. There's friction at play. But what we do see is that, in essence, the forces and the tractions are now, or the tractions at least, are not uniform anymore. They are now varying over the system. And what we see is where we have large tractions is not always the place where we have large forces. And that is because the place where we have large contact areas might vary quite drastically now. We can see now towards the bottom large fractions of large contact area for this snapshot and smaller contact areas at other places. And where we have some of those small contact areas combined with large contact forces, we end up with very large tractions. And that's in essence by growing our chain network beyond force chains towards areas and tractions, we learn so much more about particle systems and the suitability of various contact laws for application in complex scenarios like additive manufacturing. And this concludes the talk, the discussion, and hope I've distilled a couple of core concepts in terms of why we need to move beyond force change towards information chains, and why an additional example of towards force change, traction change, is a good candidate. But there are much more than just traction change and areas that we could look at. There are many, many more information networks we could look at in particle systems And the whole idea of information change is to open up that mindset to say, let's explore that space and learn as much as we can and broaden our understanding of discontinuum mechanics so that we can suitably apply them for applications as additive manufacturing. Thank you.